In this video, we're going to take a look at some properties of the Lagrange interpolating polynomial. Namely, we are first going to show that it agrees at each node. And so when we say agree, what we mean is the function value at every value x0, x1, up through xn, those function values are exactly the same as the polynomial value at x0, x1 up through x sub n for that Lagrange interpolating polynomial. So remember, our nth Lagrange, our Lagrange interpolating polynomial is built with these building blocks where lnk we have x minus x0, x minus x1, up through x minus xk minus 1. Then we skip the x sub k term, so we go xk plus 1, x minus x sub k plus 1, all the way up through x minus x sub n. And on bottom, we have the same thing, only we have, in place of x's, we have x sub k. Now again, the reason we don't have the x sub k minus x sub k term is that we've skipped over that x sub k term. That way we don't have 0 in the denominator. It keeps things working appropriately. Now notationally, we could write this as this is a product over I equals 0 n x minus x sub I over x sub k minus x sub I. So it's this product where your I value is not equal to k. So we're going to jump over the kth value, but otherwise it's that product. And so we want to argue that this agrees at each node, and so we will notice that lnk of x sub I for I not equal to k. So what would this value be? Right? So if we plug in x sub I where that value of I is not equal to k, then somewhere we are going to have on top a 0. And so because of that, we will have a 0 being multiplied by something, and that output is going to be 0. Now, if we have k, ln k evaluated at x sub k, then when we look at this product here, every single one of those, we're going to have x sub k minus x sub I over x sub k minus x sub I. So we're just going to have 1 times 1 times 1 times 1 times 1 times 1. And so that product's going to be 1. And so when we look at our Lagrange polynomial at that value at x, let's say at x sub k, oh, actually, before I do that, I should do this. For I not equal to k, ln I at x sub k, that is going to be 0, right? So like this is a special case of this. And so if we were to look at our Lagrange interpolating polynomial at, let's say, xk, then what we would have is all of these are going to be 0 except for this one that's going to be 1, and it's going to be 1, and that value is multiplied by f of x sub k. Right? So our ln k is multiplied by the function value to x sub k, and so those two values are going to agree for absolutely every single choice of k that we might make in 0 to n. Yeah, so it agrees. Another thing we might be interested in is what kind of error is there. And so the error that is associated with this, so suppose that we have these distinct numbers in the interval a to b, and our function is differentiable and continuous on a to b. For every choice of x in a to b, there's an associated number, zeta of x, between the minimum and the maximum of those values. And since it's between those, it must also be between a and b. And that value of zeta exists such that the function value at x is exactly equal to the polynomial, the Lagrange polynomial at x, plus, and then the extra stuff we're going to have is the n plus 1 derivative evaluated at zeta over the nth factorial, or rather n plus 1 factorial. But it's not just that, it also gets multiplied by x minus x naught, x minus x1, all the way up through x minus x sub n. So we have, this has unknown values of x, or has these, sorry, not unknown values, but has those values of x. This value of zeta is based on the choice of x that you might make. This right here is the error term. So the amount of error that we have, a bound, the error we have is when we approximate our function using this polynomial, that error is right here. Now, trying to figure out that error ahead of time in general is a little bit more difficult because we don't necessarily know the function in real-world kinds of settings, and so then we don't know its derivatives, and so we can't actually put a bound on that error. And so there are ways that you can recursively develop that, and so there's a method called Neville's method. And so what is Neville's method? I am glad you asked, because we're going to talk about that in the next video. I will talk to you then.